Hi everyone, thank you for tuning into today's session. I am Zing from SGInnovate. We are a government-owned organization that invests in and help build deep tech startups that leverage science and technology to make lives better for all. A big part of our work is to build a global community of leaders and doers who are driving deep tech innovations such as AI, medtech, quantum tech in our economy and society. Today, we are very happy to have Dr. Sakya Dasgupta, founder and CEO of Edge Cortex Inc., here with us to present on breaking down artificial intelligence at the edge. Edge Cortex is a deep tech startup based in Tokyo and Singapore, automating machine learning-driven AI hardware and software co-designed for an intelligent distributed edge ecosystem. Just some housekeeping notes during the presentation. If you have any questions, do leave them in the Q&A box at the bottom of your screen. So without further ado, let's bring on the star of today's show, Dr. Sakya. Sakya, please.
Hello, everyone. You can hear me and hopefully even see me right now. All right, great. So thanks for joining the call. Firstly, I hope everybody is staying safe. I know these are unprecedented times. So hopefully, everybody is at the comfort of their homes and staying safe from COVID-19. So what I'm going to do is that in order to make sure that the bandwidth does not get affected, let me go ahead and close my video, but you can still be able to hear me. I can start my video once again later during the Q&A. Okay, so today I'm going to really talk about efficient edge intelligence, but mainly when I kind of started off creating this presentation, the idea was to kind of break down what do we really mean by AI at the edge, and we'll take that journey. But essentially, at the end of the day, really what we're trying to create is how can we create more efficient deployment of AI or intelligence as we know it in edge devices. And we're going to break down and talk about what do we really mean by the edge, and how do we really bring intelligence to the edge. Okay. So let me just quickly introduce ourselves. Edge Cortex is a fairly early stage deep tech AI startup. It was founded in 2019 in Singapore and Japan. Having spent a large number of years in the industry, especially in places like Microsoft and IBM Research, I realized that there is a growing need for creating next generation hardware and software that can really deal with the large amounts of data that's being created at the edge. And for that, you also need really to rethink the machinery in terms of both software and hardware. And that led to the creation of Edge Cortex as a company. So really, in our case, what we have to offer is a unique AI hardware and software co-exploration engine, along with the dynamic neural accelerator architecture. And I'm going to talk a little bit about some of these aspects today while we discuss edge intelligence. Okay, so at the very onset, let me address the elephant in the room, which is the term AI. So though we kind of colloquially use AI or artificial intelligence, we really need to define what do we mean by AI in this context. And at the very onset, I would like to make it clear that artificial intelligence in this context, especially in the context of edge intelligence, or really in the context of the way we talk about it in the industry right now, is learning from data. Although AI as a word was coined as far back in 1955 by John McCarthy, already at that time, it was clear that there are two endeavors of AI. One is the computational endeavor, and the other really was the quest to mimic human intelligence. And when I'm talking about bringing AI to the edge, we are not really trying to mimic human intelligence on these edge devices, which would be an enormous feat. However, in our current generation technology is still quite far away from that. What we really mean is a subset of artificial intelligence that we call machine learning, wherein you typically have these algorithms that improve or learn when exposed to large amounts of data. Within that category of machine learning, you have another subgroup, which we typically call deep learning, essentially using neural networks loosely modeled on the visual system in the brain, or at least those were the early inspirations for creating many of these networks or designs. And these kind of neural networks essentially learn from very, very large amounts of data. And by training these on large amounts of data, we hope that they're going to become very good at recognizing patterns in the real world. And when I'm talking about AI, I'm largely talking about such deep neural networks or deep learning systems. So let's, with that, go ahead and kind of define what do we mean by edge computing. So essentially, if you think about edge computing right now, we should start with cloud or data center. So I would imagine that almost everybody here in the audience is kind of familiar with cloud as a concept. So you have essentially a largely centralized location with an infinite capacity of workload, and typically dealing with multiple sources. So what that means is that in the cloud, you essentially gather information from various different sources, and it's also largely capacity driven. So you have an enormous amount of compute resources available to you, and you're also have a distributed solution, meaning that your storage, compute, and connectivity fabrics don't necessarily have to be constrained on a single system. You can have diverse access to different kinds of compute, different kinds of storage, as well as different kinds of connectivity. The edge, on the other hand, is quite different. So what you see here in this namesake, the edge is essentially where the data is. Almost all devices that you can think about can be classified as an edge device or an edge computing device. So all your physical devices, so your sensor devices, your visual audio devices that are collecting vast amounts of information continuously, for example, a mobile phone, even a car or a robot that is disconnected, let's say, from a centralized source of information, but has some form of capacity to gather information on the device itself, would be classified as an edge computing device. Are you able to hear me now still? I see some messages that it was not clear. Awesome. All right. Okay, great. So on the second level of edge intelligence, you not only have the devices, but a little bit further down and still away from a centralized source of information like a cloud, you have what we call the infrastructure edge. These are your typical gateways. They have a little bit larger compute capacity than the device itself. However, they are limited by the workload, and they are also limited by the resources they have access to. So fundamentally, what separates the edge and the cloud is that edge devices are essentially resource limited. And if you want to deliver the same level of performance that you have in a cloud, the only real handle, the only real knob that you have access to is to improve the efficiency. And largely what I'm going to talk about today is ways in which we can essentially improve this efficiency in order to match the same level of performance that you get on a data center using edge devices. So before we kind of go forward, let's kind of talk about some numbers, some statistics. So why edge intelligence now? Why should we actually bring intelligence to the edge? Essentially, by bringing intelligence to the edge, you're bringing intelligence to the very seat of data. Your edge devices are where your data is being curated. By some measures, we expect to have 79.4 zettabytes, that's 10 to the power of 21 bytes of data in 2025. Just to put it in perspective, by some measures, if you were to count the number of sand particles in all the beaches in the world, that would be equivalent, or your 79.4 zettabytes would be larger than all the sands put together. That's a huge amount of data that's generated by 2025. Interestingly, recent studies show that 75% of all this data is going to be processed outside the traditional data center or cloud. That largely means that today, a lot of the data that is being centralized, it's going to move out and get distributed to all these different edge devices. So absolutely, we need some level of intelligence on these devices itself. If you talk about the market itself, it is enormous potential. A recent study from Practical shows that 56.5 billion USD of projected edge AI chip market value by 2025. which would be 3 times larger than the chip market that we have, or the equivalent AI chip market that we have today for data centers. So it's an enormous market value that one can capture by bringing intelligence to the edge. If we now talk about the applications, there is a huge number of different industry verticals that is already being fueled by edge computing, bringing both better services, more safety, reliability, as well as efficiency to almost all these different verticals. So, if you take a look at now some of these, specifically some of these things that are taking advantage of edge computing in various applications. For example, in smart cities, analyzing traffic and parking, LPR, typically known as license plate recognition, is already being widely deployed in many places, including Singapore. If you take a look at robotics and manufacturing, one of the biggest impacts has been in detecting defects in real time with very high accuracy. Now, if you think about humans, we could detect such defects with perhaps up to 70 or 80% accuracy with a highly trained eye. However, if you now have the capability to use machine vision directly on these devices at the edge, we could achieve 99% or even higher accuracy in detecting defects. That directly translates into better quality of products, as well as a massive cost savings in our manufacturing process. If you think about healthcare, right now with COVID, we have already been exposed to the shortcomings of our current infrastructures in many places. Recent movements has been towards bringing, for example, portability to many of our diagnosis capabilities on the device itself. For example, portable X-ray machines could be widely deployed in various places relatively fast and cheaper than having a much more centralized source of that kind of monitoring and diagnosis capability that we have currently. And all of them is really being fueled by edge computing. If you take an example of agriculture, I believe that's going to be, again, a huge marketplace that is getting disrupted by edge computing, both in terms of all the different types of IoT, Internet of Things sensors that are available to kind of track the growth and monitor agricultural development, agricultural growth, as well as in terms of large autonomous systems like autonomous harvesters that can really supplement or make it much more efficient the human labor that we have currently that goes towards agriculture. So overall, across industry verticals, the impact of edge computing is tremendous. However, although edge computing is really impactful, there are some large challenges that we need to deal with. If you now look at the slide, what we are trying to kind of understand here is the optimal compute architecture that you would have. It really varies across applications. If you look at autonomous driving, for example, the need for processing speed or your energy consumption, flexibility, or even the amount of dollars spent, that is the amount of cost that you would want to bear in order to implement such on-device processing, vastly varies from other applications. For example, if you compare it to face detection. Not only that, edge computing on these devices also varies in terms of whether you're actually doing training. That is, are you learning with these deep neural networks on the device itself, or you're performing what we call inference. The critical difference being that in case of inference, you have a neural network or model that has been trained on vast amounts of data already. The parameters of that model is now fixed. You're not really making changes to those parameters. You're now only consuming data in the real world and generalizing in order to identify patterns that it has been trained to identify. And just to make it clear, throughout this presentation, when we are talking about intelligence at the edge and our current capabilities, we are really talking about effective, efficient inference on the edge. And clearly, as we can see already here, the compute requirements greatly varies across different applications. Things get even more stringent. So in order to bring intelligence to these devices, there are really some strict constraints, both in terms of software and hardware, that one needs to adhere to. Some of these are really fundamental. So we discussed some benefits of edge computing, but what are these strict requirements? Now, for example, let's say you're going to run a pedestrian detection algorithm on your car. We are discussing autonomous driving. You can't just have a tiny, let's say 16-bit controller that's running your refrigerator at home. It needs quite a beefy processor to run this AI algorithms, typically with trillions of operations at high resolution. Now you can't do this at the expense of enormous energy. So you not only need diverse compute requirements with large numbers of or trillions of operations at full HD resolution, you also need to have strict budget of your energy consumption. Some of these numbers I should make it clear that these are definitely not minimum or maximum values. These are ballpark figures, but these are the numbers that you would typically look at when you're deploying a solution on the edge. And this would also vary depending on whether you're deploying for a smartphone or you're deploying for a self-driving car. So you not only have diverse compute requirements and energy efficiency requirements, you also want to have real-time performance. That essentially means low latency. So let's say you have a camera that is, real-time recording images. If you now gather all that data and send it to the cloud, that is going to have an enormous latency impact, which will affect your real-time performance usability. Last but not the least, you have two more fundamental requirements. The first one being low cost. When you're deploying on the edge, essentially it's a scale issue. Since you have a lot more edge devices than you have a cloud data center, you really need the cost of these different components that create your edge devices to be extremely low. And lastly, data privacy is of paramount importance. Since you're on the device, you can control the amount of information that you locally consume versus what you send to the cloud. Now you would want to have a handle to what is the data that you own and what are you comfortable to share to a centralized server or a data center. So let me try to break down the cost analysis with a simple illustration here. So for example, let's say you have a single camera that is recording some images, let's say a surveillance camera. You typically do some kind of encoding directly on this camera, but you gather all the data and send it off to the cloud, both for AI processing as well as memory. In this case, you are not only having to deal with the bandwidth, the latency constraints of sending gigabytes of data, and in some cases even petabytes of data, for example, in the case of an autonomous vehicle, but you also have to pay an enormous cost for AI processing on the cloud. By some measures, so in this case, we are taking a modest estimate of, let's say, 10 cents per GB. This would come out to somewhere around $500 a month for a single camera. On the other hand, if you have an efficient edge device, you have a chip that can, on the device itself, on the camera itself, process all the information, and then send some metadata off to your cloud, essentially selectively send some data, but largely processes all the information on the device itself. You can completely avoid the AI processing on the cloud, and you're only literally paying for just the storage requirement. So in this case, it would be some 500x saving of the amount of cost that you would bear per month. So essentially, you're bringing down your cost, you're bringing down your latency, so you have real-time performance. And lastly, as we already discussed, you can now keep all that data quite private and only share some amount of metadata that you're comfortable sharing. So essentially, it's a no-brainer that from a scalability perspective, from a cost perspective, edge intelligence is really the only way we can scale up and bring the power of deep learning and AI to all these different devices. However, now if I want to now bring machine learning and AI to these devices, there are still further challenges, not only these strict constraints, but the challenges of compute required for today's generation of deep learning is also something that we have to bear. So in this chart, what we are seeing is essentially on the x-axis, you have since 1955, 1960, the creation of perceptron, essentially the simplest neural network that we could think about to today in the modern era, where there essentially has been an exponential rise in terms of the capabilities that the networks have, but that has also directly resulted from the need for compute. So it should be apparent that your y-axis here is essentially the petaflops per day's requirement. And although you see a linear curve graph here, this is really an exponential curve. If you juxtapose this with essentially something like Moore's law, that since 1975 has essentially seen doubling of the amount of transistors that we can put in a single unit area per unit cost, double every 2 years. In the modern era for these deep neural networks, we have seen a similar doubling every 3 to 4 months. So really, we cannot keep up with the amount of compute need for these kind of deep neural network training. The matters get even worse if you now think about the impact that this is directly having on the environment. Training of a single AI model can emit as much as the carbon emission equivalent of 5 cars of lifetime, which is essentially something that we cannot continue to sustain if we want a healthy climate, a healthy planet. So largely, we not only have those constraints that we need to deal with from an edge intelligence perspective, we also have to come up with solutions that allow us access to better compute and deal with this complexity, the training complexity issue of these models. If we now go ahead and try to create a better chip, so we have already kind of established that really it's a no-brainer to bring intelligence on the device itself. That would mean that we need to create better hardware, better chip on the device. But then again, we have few challenges. So on the left-hand side, what you see here is the performance density of our chips, of semiconductors has really stopped growing. It has stopped scaling. And this curve is up to 2017 with a 12 nanometer in process. We have had some success now, having moved to 10 nanometer, 5 nanometer. So that has been, some significant growth. There has been talks of a 3 nanometer process. It hasn't been realized yet. However, we are already hitting the limits of what we can do in terms of performance density. Along with performance density, as we already established, memory or energy efficiency is critically important. And the story is similar in that case. Both the energy efficiency of our memory, in this case, what we call dynamic RAM or static RAM, SRAM, both has really stopped scaling since a long while. And already, although we have again access to smaller processes, the ability to essentially have better energy efficiency of this memory has really decreased over the years. Now, bringing all these things together, it really is a challenging problem to realize edge intelligence. So how do we really deal with this problem? Okay. The final challenge that I would like to expose is the need for flexibility versus efficiency. So what you see here is essentially depicting largely current generation hardware that can be broadly classified into these 4 categories. And you have various degree of flexibility. So in this case, by flexibility, we mean the ability to essentially effectively program these different devices. In terms of flexibility, CPUs or central processing units are essentially the most flexible. However, they're also the least efficient in terms of performance, size, or even power. If you go towards GPUs, so these are our graphical processing units. These are heavily used in the industry right now for deep learning training, as well as for inference in many cases. They are more flexible as compared to a CPU, but still consume a significant amount of power and energy that is not sustainable when it comes to the edge. If you go all the way to an ASIC, you essentially have very little flexibility. It's hardened silicon. Once you have fabricated the chip, you essentially typically cannot make changes to its behavior. However, because you sacrifice flexibility, you gain a lot in terms of efficiency. So the question is there a middle ground? Is it possible for us to create essentially next generation hardware that still retains significant amount of flexibility without sacrificing efficiency? So for that, we would like to essentially propose a solution, and I would like to walk you through those steps. So the different constraints that we talked about, we already established that efficiency is the key for realizing edge intelligence. And if you want to really bring both the capability of flexibility as well as efficiency, one of the solutions that we can think about is essentially a co-design or a co-exploration paradigm, what we are calling an automatic AI software hardware co-design, which essentially means that you're concurrently designing and optimizing several aspects of your system. In this case, both the hardware and the software. If you think about deep neural networks, your software is essentially the algorithm that you're dealing with, and the hardware is the substrate on which you would run that algorithm. Current generation work has essentially has been constrained by the fact that you create your algorithm separately, and then you have to retrofit that algorithm on existing hardware. However, if you take a co-design approach, from the very onset, you can add constraints on metrics like throughput, latency, power, and size, which we have already established in the key constraints for edge intelligence, in order to design both your algorithm as well as your hardware. The critical point here being automatic, meaning that we would like to use the power of machine learning algorithms itself in order to do this kind of a co-design process. If we leave it to completely human design endeavor, that again becomes an extremely large search space that we would have to deal with. Secondly, what you're really optimizing here is that you're optimizing across architecture strategies. What that means is almost all, if not all, current generation general purpose compute are essentially based on what we call the von Neumann architecture. And they're all essentially control-oriented architectures. That means the largest amount of your energy expense in a general purpose compute is spent on essentially the control and not on your compute and memory. And I would recommend referring to the study from Horowitz in 2014 that really details what are these different energy barriers that we have and how we could potentially overcome them. Having such a co-design solution where you can automatically search through the space, you could search through different architectures that are not control-oriented. The reason this is important is deep learning or these kind of neural network architectures are essentially extremely lean from a control perspective, or I would even say there is no control that is required. It's largely the compute, the data flow, and the memory that you have to optimize. So you can really not only search through that space of the models, but you can also search through different types of architecture strategies. You could be compute limited. So for example, in this case, you limit the amount of compute that you have. You could optimize some other parts of your memory. You could also be weight bandwidth limited, meaning that you bring your data onto the device itself, and then you could reuse that data multiple times. You could reuse the parameters of that network multiple times. And similarly, there are various different strategies that one could try out. And in this case, having a co-design framework, you could search across various different strategies. Now, even before we can go ahead and break down what such a co-design framework would look like, I would like to kind of bring to your attention that this co-design or the co-exploration solution space or even the search space is extremely vast. You not only have the software space, which is typically your AI algorithm that would work with some kind of framework. In case of machine learning, we typically use some open source framework. It could be PyTorch, it could be TensorFlow. And then you also have to deal with the complexities of a compiler, essentially something that can translate that high-level program written in, let's say, Python to a language that a hardware can understand. On the hardware side, now you have, again, a very vast space. You not only have the system architecture, how should you arrange the different parts of your compute memory all together in order to create an architecture that is very efficient, as we already discussed. You have also potentially this search opportunity on circuits and device physics. So you could potentially even search for next generation materials or even memories that allow you to get much better performance. However, if you can constrain yourself to certain parts of the search space, so in this case, we are going to constrain ourselves to essentially looking at the AI algorithm as well as the system architecture, assuming that we are still using current generation circuits and device physics. We are not trying to create essentially looking for a material that is far out there and not being used as an industry standard currently. If you kind of fix yourself or constrain yourself to that search space, it largely boils down to the things that you see here depicted in red. So you could now search for, you can use techniques like neural architecture search, and I'm going to talk about this a little bit later, in order to design better algorithms. You can automatically now try to compress these models in a form that they can fit within those resource constrained environments that you have on the edge device. And then you can also use various other techniques that allow you to leverage or increase the performance of your hardware. So effectively, by having a knob where you can now use an algorithm to search the space rather than a human having to go ahead and search the space manually, optimizes significantly what you can achieve, as well as the time constraints that you would have in order to realize such a solution. So with that, let's go ahead and look at how do we really automate deep neural network software and hardware co-exploration. And I'm going to start walking you through one such solution that we came up with in terms of realizing such a co-design framework. So before we can actually talk about co-design, I would like to go through what I call the journey towards automated co-exploration and really look at an evolutionary path of current generation deep neural networks, current generation algorithms. So although, as we have already established, neural networks started all the way from perceptron in the 1960s, 1955, it's really post 2012 that with deep neural networks, we have started achieving significant performance that has in many cases surpassed human performance as well. And the names that you see here, like AlexNet, VGGNet, GoogleNet, these are essentially different types of neural network that were hand engineered from various different places, academic labs as well as industrial labs. And if you go from 2012 to 2020, there has already been a shift towards very large, heavy architectures to more leaner architectures like MobileNet that are already designed thinking about making them much more friendly to resource constrained environments. However, it is still significantly very difficult for human engineering to come up with modifications to these architectures continuously. In the next generation, since early 2017 or late 2016, we started using what we call AutoML or neural architecture search, essentially using algorithms, using AI algorithms itself in order to search the space of these neural networks. So each neural network, now you can think that they are composed of different components like neurons. Each neural network could have different layers. You could have different types of neural networks like convolutional neural networks or recurrent neural networks. What AutoML talks about is having a search algorithm, or you can think of this as a hyperparameter tuning mechanism that allow you to effectively sample different types of components that create or build up a neural network, and then optimize that for a particular task. That led us to creating what we call hardware-aware neural architecture search, meaning that we quickly realized that it's not enough for us to just try to optimize the algorithm. At the end of the day, as you've already established, you're going to kind of deploy these neural networks on a device, let's say on a cell phone, on a mobile phone, that has limited amount of energy. It has limited amount of memory. That means even if you have a very highly accurate model that was designed in the cloud, it's not necessary that it would satisfy all those constraints on the edge device. So what hardware-aware search talked about is, can we just add those constraints in the form of some objectives during the search process that the neural network not only optimizes the accuracy, it not only becomes better in accuracy of those models, but also tries to satisfy typically constraints like latency. However, in this case, you're really constrained by the architecture. meaning that, let's say you have a cell phone once again. In that case, the hardware is really fixed. So if I know a priori what my hardware is, I can add some constraint in terms of latency. However, using this process, I can optimize the neural network for that given hardware. I cannot design a next generation hardware. That led us to creation of what we are calling the fourth generation in this evolution process, and what we call this co-exploration neural architecture search, that wherein we not only should have the ability to search the space of the neural architectures and design better algorithms, but also be able to search the space of the hardware design itself or the hardware accelerators itself. This would mean that you need some substrate, you need some capability to add a hardware constraint, as well as use those constraints to design better hardware while you're actively searching for better models itself. So I'm going to walk you through essentially what this kind of a co-exploration or co-design framework would look like. So as we've already established, if you're now thinking about co-exploration, you're performing two objectives. You're not only searching the space of architectures, you're also searching the space of these hardware designs. That means in the left-hand side, you now have essentially an algorithm that would effectively sample from various different types of neural networks, which is the same neural architecture search that we have been using since 2017. And you have some objective accuracy. So at the end of the day, these neural networks need to be designed such that they get better and more accurate for a particular domain, for a particular application. At the same time, now if you have essentially a substrate, if you have a hardware wherein you can create different types of templates, different types of designs that can specify, let's say, chip area, latency, processing elements, memory, as well as precision, I could now effectively search the space of the hardware itself. These are the constraints that we essentially need in order to realize intelligence on the edge device, as we have already established. However, the major constraint that stopped us from innovating in the space has been, what is this hardware that we could actually use to search? And essentially, we had already such a hardware available to us that allowed runtime reconfiguration, or rather, essentially the ability to make changes to the properties, the behavior of that hardware. And this is essentially a class of hardware that's known as FPGAs, or field programmable gate arrays. And you can use them to essentially search for better accelerated designs. So at the end of the day, you would essentially have a neural architecture that you started off with. You would use an AI algorithm, and this could be essentially a search algorithm that is as simple as random search, or it could be as effective as or as complex as a reinforcement learning algorithm that essentially learns through trial and error and searches through the space of both your neural networks as well as the hardware design. You continue doing this multiple times until you essentially find a solution that satisfies both your accuracy constraints as well as your efficiency constraints that comes from the specifications that you have already provided in terms of your edge device. And at the end of the day, you end up with both an energy efficient neural architecture as well as an energy efficient hardware design. And in this case, we recently published this paper to showcase how one would realize this architecture. I would reiterate that point once again to kind of bring home the message that fundamentally, because we are constrained by the fact that Moore's law has stopped growing at the rate it was growing historically. Secondly, we have constraints in terms of the complexity of these neural network models. And thirdly, we need to essentially design systems, we need to design algorithms and architectures that can work within resource constrained environments of our edge devices. We need a solution that is really automated rather than hand design, rather than completely human design. And that's one reason why such a co-design framework works very well, in order to be able to search the space automatically. Okay, so without getting into too much details of how one could kind of implement this, let's look at some results of what such a platform would actually offer in terms of an edge AI solution. So what you see here is that you can use such a co-design framework in order to satisfy diverse constraints on both your latency as well as of accuracy, meeting the strict constraints that we have already kind of laid out for edge AI. The blue dots that you see here is essentially obtained using co-exploration. In this case, you're running this algorithm multiple times, sampling format for essentially a typical standard task like ImageNet, which is essentially a task that is used in academia in order to come up with or design better neural network architectures. The red triangles that you see here are essentially obtained using a similar algorithm, however, without the co-exploration component. That means you are now constrained by a fixed hardware design, and you're only adding constraints of latency and your efficiency constraints for that fixed hardware, what we call hardware awareness. And clearly, if you essentially use such a co-exploration framework or co-exploration design strategy, then a significant shift in the Pareto frontier can be achieved. So essentially, a Pareto frontier is what you can get by looking at the highest, let's say, the lowest latency and highest accuracy for, in this case, for this algorithm versus this algorithm. You can effectively reduce your latency significantly as well as increase your accuracy. And that directly translates into, again, cost savings, as well as matching the performance that you would get from a data center directly on the edge devices. In this case, we are implementing this solution on an edge FPGA of, in this case, Xilinx, but you could equivalently use the same design and directly fabricate that into a full ASIC, having satisfied the constraints that you had started off with. Now, of course, one would wonder that, okay, here we are really talking about latency, but when we discussed edge intelligence, we talked about other constraints like energy and even area. And you can actually scale up this entire design process to look at an even more complex search space where you're now searching through a much more high dimensional space of including your latency, energy, as well as the chip area. So effectively, ultimately, you would want to have really low latencies to get real-time performance. You would want to have low energy requirements in order to increase your power efficiency, as well as you would want relatively small chip areas such that you can essentially have a lot more compute capabilities with the same chip that you're deploying on the edge side. And using a co-design framework, you can really achieve such optimal solutions that is very difficult to achieve using heuristic search or even human design endeavors. And the whole objective here being that using such a simple framework, one can move all the way from a neural network that was previously really designed without thinking about the hardware, and go all the way to design both a better hardware framework, a hardware accelerator that really fits hand in glove with an efficient neural architecture. What I did not talk about particularly is the impact of bit precision. And I just wanted to quickly highlight that when you're really deploying solutions on the edge, there is also another knob, another handle that we can tweak. And typically this is the handle of the bit width or the precision of our operations. What that really means is, if you think about, let's say, a current generation computer that you're using, typically you're performing operations in 32-bit, in floating point operations in 32-bit or 64-bit. That really means that you have 2 to the power of 32 different possibilities to represent a given number, okay, or given value. Now, if I reduce that to 8-bit, that means I now have 2 to the power of 8 possibilities to represent that same number. You have effectively reduced, by reducing the precision, that really means that you have less requirements of memory because you have effectively compressed the space, but typically you're also sacrificing some amount of accuracy. And what you can see here already is that if you compare the throughput requirements, so in the edge side, as we have already discussed, you would want to have high throughput, and at the same time, you want high energy efficiency. And being within around 8 bits of precision, you can really achieve very high combination of throughput and energy efficiency. In fact, recent studies, so this is from the ISSCC conference, which is one of the leading conference of solid state circuits in 2019, showed that there have been some implementations that even with a 16-bit precision, so 16-bit fixed point precision, or even at times with floating point operations, can achieve very high throughput and energy efficiency. I would say that the 1 bit, although it looks really good, one of the drawbacks of using 1 bit, this would essentially mean that you're representing everything in terms of zeros and ones. Now, although we can really compress a model significantly, you would really bring down the memory requirement drastically, but typically you would sacrifice your accuracy significantly. And it really depends on applications, but majority of applications like healthcare, or let's say transportation or automobiles, accuracy is something that you really don't want to sacrifice. So that's, again, a trade-off that you would have to deal with in order to be able to design better algorithms as well as hardware, such that your hardware needs to support or essentially have high energy efficiency and still have high throughput without sacrificing your precision. So all of that is great. So, we have essentially defined now, how do we hopefully tackle this challenge of creating more energy efficient systems or devices that can realize intelligence on the edge. But really what we haven't really talked about is this aspect of flexibility. And at the very onset, we talked about our current generation general purpose computes like CPUs being extremely flexible in being able to program that very easily. So it's really also possible to use the same framework and create systems that are also extremely flexible. And in this case, the co-design framework that we end up creating, you could essentially design these systems once and deploy them flexibly in various different devices. So in this case, you would start with a deep neural network framework like PyTorch or TensorFlow, current generation state-of-the-art deep neural network frameworks. You would essentially perform, as part of an automated co-design engine, your neural architecture search as well as your hardware design. In this case, you could add your constraints in terms of your chip area, your latency requirements, your memory requirements, as well as your requirements in terms of precision, and search that space collectively. Having searched that space, once you compress and potentially quantize these models, meaning that you reduce your precision by a certain amount, you can essentially pass this off to a compiler. In this case, what we realized early on is that when you're trying to create essentially a hardware that works effectively on the edge side, you also really need a very strong software ecosystem that can leverage those capabilities. And in this case, building on top of state-of-the-art open source compiler like TVM, you can really extend the capabilities that you can get with such a co-design framework. So in this case, once you have searched, you could import that model and compile that once, such that a single model once compiled could now be deployed on various different devices. You can compile this same model and deploy them effectively on CPUs or x86 architectures. You can deploy them on ARM processors running, let's say, on a smartphone or other small factor devices, or you can also deploy them directly on GPUs. Using a custom backend or Accelerator backend, in this case, this is a custom API that would be based on the specifications that you would get for an accelerator that you've created, or a new hardware design that you have created. You could essentially use the same deployment module to directly deploy that model onto the neural accelerator itself. So meaning, all that you have to do is you have to essentially, you have the ability to co-design once and then deploy flexibly on various different devices across current generation hardware as well as next generation accelerator like our dynamic neural accelerator. So having created this system, just wanted to highlight, although we have still just only been scratching the surface in terms of what we can do with such a co-design framework in order to realize intelligence on edge devices. We call this accelerator the dynamic neural accelerator, or DNA. Essentially, this was designed from the ground up using such a co-design co-exploration framework, and specifically created for deep learning on the edge. As we said, you have to adhere to the strict constraints that edge intelligence brings you. In this case, low latency. So essentially for deep neural networks, you have the ability to run a batch size of 1. That means single frame latency directly on these devices. You essentially now have access to high performance, potentially up to 24 tera operations per second at a 2-watt energy requirement. That would translate to somewhere around 12 TOPS per watt, which would essentially bring this kind of a framework to be the current state of the art of what is possible right now with existing edge chips or edge architectures. You can essentially also get very high efficiency. In this case, each operation can be performed under 0.1 picojoules. That effectively also allows you to remain within those resource constrained environments, but yet get high compute capabilities. You can also have ultra scalability. That essentially means that you're not restricted to a single accelerator or a single chip. You can essentially have a chip with multiple cores, multiple such accelerators put together. You can also arrange multiple such chips together to create a larger configuration. Why that is essential is that now if you take that same solution, the same accelerator, and deploy that on an environment like a smartphone, typically you have very different resource requirements or restrictions as compared to, let's say, a self-driving car. So in a self-driving car, if you're dealing with around a few hundreds of watts, you can still scale up the same system and get an energy requirement of, let's say, tens of watts and achieve the same level of performance. And you can scale down effectively and go to the smartphone with a single core and again deliver the same level of performance within a much more smaller footprint of energy requirements. Last but not the least, you can also have flexible usage. In this case, you would effectively not do any kind of low bitwidth training. Now, why that is very important is, as we already discussed, if I now change my bit precision, the bit width, you could effectively compress these models very well, but you could also sacrifice accuracy. And one way of doing this is while you're training your models, you can essentially train them in low precision. However, now let's say, let's take the example of a manufacturing process where you're trying to, you have a camera that is trying to essentially identify defects. Typically, you already have an existing model. It's very difficult to take that existing model and also have access to all that data and retrain that model with low precision. If you can take that existing model without making any changes to that model, you only do post-training quantization, like what we have seen here in this kind of a framework. You can essentially not having to deal with retraining or even access to the vast amounts of data that are typically proprietary to any kind of industry applications. Last but not the least, you also want requirements or ability to program these devices very effectively and easily. And using essentially an easy combination of an effective compiler system architecture as well as the co-design framework, you can program these accelerators directly in your high-level programming languages. As a machine learning engineer, and if you're trying to deploy an intelligent solution on the edge, you're effectively writing your program still in your favorite, deep learning framework. In this case, let's say in Python, and all the complexity of taking that code and deploying it on the edge would be handled by an intelligent compiler. And that's really important if you want to scale up solutions on the edge. So what you can really do is, this is one example of what one can achieve having such a framework. So you could effectively have various different applications running in high resolution simultaneously under very significant energy constraints without using any kind of current generation GPU and yet achieve real-time performance. This would have been a video, but given bandwidth restrictions, you can go to this our YouTube channel and take a look at one such example where this is a typical scene from Akihabara in Tokyo, really crowded scenes typically during the day, and you could effectively perform real-time applications directly on an edge device using such an accelerator. So with that, let me essentially summarize what we talked about. So what I really wanted to highlight in today's talk is edge intelligence is really where the action is. It's really a no-brainer in terms of the cost effectiveness of bringing intelligence on the edge, as we already talked about, if you compare it to a data center. But there is really a significant amount of challenges that we need to deal with. And typically these challenges are challenges of energy, latency, and power. So, or energy, latency, power, and cost. So you can also think about energy and power together. And in order to deal with that, you also need the ability to redesign your neural networks. And since current generation neural networks are heavily constrained on compute, you really need to rethink how you're going to design both your algorithms as well as the software. And the way I see it, the future of AI is really at the edge, and co-design is imperative in order to create these kind of novel architectures. And although right now one would focus on efficiency, really there is no limit to think about next generation materials or even memory to be included during the search process. So with that, let me essentially stop and take some questions. And thank you for listening.
Yes, thank you, Satya. So if anyone has any questions, please leave them in the Q&A box in the bottom of your column. Yep, Satya, I think there's already 2 questions, and there's one question on the chat box currently.
Let me see if I can go to. So let me go ahead and stop sharing. And all right, so okay. All right, so let's see. So after we have a 5G network and speed, the value of edge computing will be greatly diminished, except only in remote areas where we don't have 5G coverage. Okay, that's a great question. So let me take that. So essentially, I would really disagree with that fact. I think 5G really would accelerate edge intelligence, and there is a very simple reason for that. Now, even if you have 5G capability, it really does not do away with the fact that you have cost requirements. So perhaps you can bring down your latency requirement to a certain extent, but your cost is still going to be significantly high if you want to process all that information on the cloud. Secondly, you're still not able to do away with the privacy requirement. Ideally, you would want to process this information directly on the device and only share metadata to your cloud or data center. Thirdly, if you now think about applications like self-driving car, you're typically generating petabytes of data. Even with 5G, and let's say with 5G, you have enough 5G hotspots available everywhere. Given that 5G is a very small wavelength technology, that would mean that every few meters, you would need a 5G hotspot that is available in order to sustain such a bandwidth. Passing all those petabytes of data to the cloud and processing information is going to be still a huge bottleneck. And that's one reason why even companies like Tesla, who have not been traditionally chip makers, have taken the path of creating essentially their own accelerators, their own chip dedicated for their cars. Do you believe a DNA is a tool which will be used for the build-up to hard AI? So that's an interesting question. So I would be skeptical to say whether we can achieve, let's say, human-level intelligence. I believe that's what you're hinting at when you're talking about hard AI. However, there is a lot that can be done, such a co-design process. Whether this same co-design algorithm can be scaled up all the way to a human level intelligence, I do not think so, given that we still do not have existing tools that are sufficient enough to take us all the way there. perhaps current generation deep neural networks will not have the ability to reach human level intelligence. However, we will be able to achieve a lot more. One thing that I did not touch upon is, let's say, in the case of chip design, even after you have created a good architecture, there is also a lot more that needs to be done in the actual design synthesis of that or actual placement and routing in order to create a full chip. And already we find that such a co-design framework using technologies like reinforcement learning can also be used in order to find out what are the better paths, the better routes that you need in order to deploy, in order to implement that architecture on the chip. You can think of this as finding routes in order to plan your movement through a city. In the case of a chip, you essentially you are at a very small level and you have various different paths that you can take, some less optimal as compared to others. And I find such co-design to be directly applicable in those areas. Hard AI, perhaps not in the near future. All right, so let's see. Okay, I see quite a lot of upvotes for the words, a bit small. Can I have a copy of the slides? Yeah, so I think this session is being recorded. It's potentially going to be shared later on with the participants.
Yes, this will be shared with the participants later, so do look out for a thank you email. Yeah.
All right, so so the question on, can you please elaborate more on transforming a trained model to a new device, a slightly modified architecture? I assume that, as you mentioned, we don't have access to all training data. Or that's a great question. So in this case, okay, when you're doing the co-design process, you would essentially need access to at least some amount of that original data. Essentially, this could be a subset. What I really meant was in terms of quantization, that is, so when you're trained that model completely, if you want to change, let's say change the precision, you would definitely need access to the full amount of data that the original model was trained on. That's not the case here. However, you are essentially searching for a better architecture as well as a hardware. You typically start from a backbone model. This is a model that already exists for your application, and then you can use that to create better architectures that satisfy all your energy constraints for the edge device. This is something that would be possible through our framework as a service that one can essentially come in and start from their existing backbone models. So yeah, so in this case, although I specifically did not focus on our customers here, and I wanted to kind of elaborate and talk about the broader problem of edge intelligence, in this case, our direct targets are enterprise customers. We don't right now work with individual clients, so we would directly work with large enterprises in verticals like automobiles, healthcare, or robotics and manufacturing. So let's see, there's another question from Jose. I think exploring all the research spaces means a lot of training models and testing the accuracy and performance. How can you tackle such challenge? Yeah, that's a great question. And in fact, a lot of that can be simplified to the fact that there is a lot of data usage as well as a lot of architecture reusage, meaning that once you have trained your models on one particular domain, you can really make use of that in a significant manner when you're trying to apply that in various other places. So for example, let's say you have a baseline model that was trained on detecting objects for a pedestrian detection scenario. And now you have essentially an application where you need to identify defects in real time in a manufacturing plant. You can already start with that baseline architecture, and a few simple modifications to that architecture will give you very high accuracy. And that's essentially, in a nutshell, some techniques, or what we also call transfer learning, that is essentially used in order to simplify that design process. All right, is DNA commercially available yet? No. So right now, DNA is in the form of an IP. We expect to essentially have, first versions of our IP available for some demos and testing as early as this summer. And we are working very hard, essentially, to scale this up and having a full-fledged deployment as a chip as early as early next year. I see a question on issue of data being proprietary and companies asserting ownership over them. Is there any way to prevent or address this, perhaps by coalitions or networks working together? Yeah, Arvind, that's a great question. So I think that's typically a challenge for all of machine learning and deep learning right now. It's very difficult to kind of circumvent that problem. I think one way to do this is, as you rightly pointed out, is that there could be coming together of various different organizations. However, data being really the current generation oil, people would want to kind of protect that. One way we circumvent that problem is essentially giving access to such a code design framework using APIs, where people can still be within their own private clouds and not having to share that proprietary data, but still make use of the service. And that's essentially a path that has been taken in the industry right now, and I don't see that changing anytime soon. Now the question is, can we still have access to such a co-design framework for, let's say, in a public cloud for small scale application? I think absolutely, that's definitely something that is possible. However, the scalability or robustness of those solutions without being exposed to significant amount of proprietary data might be limited. Okay, I see another question from Ryan that I'm happy to take. Could multiple DNA be organized on one piece of silicon in order to use multiple neural networks? Yeah, absolutely, Ryan. So that's essentially what I meant by ultra scalability. Already these kind of DNA accelerators can be either arranged in what we call multiple cores. That means, let's say you think about a typical CPU. You can have a single core CPU, or you can have multiple core CPU, let's say a dual core CPU. So you have access to essentially the same accelerator, but multiple instances of it in simple terms. You can also arrange multiple such chips in a multi-chip configuration, wherein they scale up enormously. Like having DNA which compares results or combined results from other DNAs. That's an interesting prospect. So when I showed that application on, let's say, face recognition, segmentation, as well as post detection, the whole point being that having such scalability and the ability to have access to significant amount of operations within a small amount of energy requirement, you can now potentially run multiple these applications at the same time at smaller of your accelerator. So it's not necessary that you have to use the entire accelerator, and you can also partition, as I already said, these accelerators into various different components. You can run them as multiple cores. So it is definitely possible to run number of different applications or diverse applications at the same time. I should mention that current constraints would potentially be in terms of the same type of neural networks. In this case, if you're running vision algorithms with convolution neural networks, or if you're running speech that uses convolutions, as well as vision that uses convolutions, you could run them on the same accelerator. It would be a lot more challenging if you're running two different types of neural network, let's say a convolution as well as a recurrent neural network at the same time. But it's still potentially possible, just not with the current architecture that we have been looking at.
So thank you, Sakya, for your wonderful presentation and to answer all our attendees' questions. So do you have any closing words?
Thank you. I hope I saw that there is quite a lot of questions. Unfortunately, I could not take all of them right now. I'm happy to take more questions. This is really a very exciting area, and I see it's really one of the most exciting times to be in the hardware space, given that a lot of the intelligence is directly coming on these devices. I'm happy to take any further questions if you just shoot me an email. And thanks a lot for joining this call, and stay safe.
Yes, thank you so much, Sakya. If you just hold on for a minute, we would just like to take a picture to commemorate today's event. Yeah.
Sure.
So do just stay on and do a little wave so that we can just have, okay, 1, 2, 3, cheese. Thank you so much. And we will direct all inquiries to you if any of the attendees have any more questions. Thank you so much for the presentation today, and stay safe and stay healthy.
Okay. Thanks a lot, guys. Thank you. Bye-bye.
Bye-bye.